Welcome to a video on non-linear limiters. So, in this video we will be looking at how non-linear limiters work, how do we design them, do some simulations, and look at some alternatives. All of this we will be implementing um, on its own and on a Wien-bridge oscillator. Okay, so automatic gain control circuit looks like this. Okay, so these two networks are voltage dividers. Together with a diode selects the positive and negative limit for the output. Okay, the moment that the limit on the output is reached, one of these diodes will activate. Okay, and in the moment that, let's say, the stop here activates, is that we have a path through here, making that RF and R3 is in parallel with one another. Okay, so the moment that the limit is reached, our gain will change. Okay, so typically the gain of a circuit, this is an inverting amplifier, so the gain of this will be RF over R1 inverted. But the moment that the signal goes past one of these limits, it will be RF parallel to R3 over R1 or RF parallel to R4 over R1. And these just sets the voltage. Okay, so these we use to limit the oscillator's output to a certain voltage, and we control the gain, pushing it from being an unstable system to a stable system. Right. So, if we do a DC analysis of a limiter like this, this line here is our input, this is our output. So within this range here, our system is unstable. Okay, so that is where we start our oscillations. But the moment one of our limits is breached on the output, our gain decreases for the positive and the negative cycle. Okay, and with our gain going down, we push our system to be stable again. Okay, so we have three different gains in this section right here. So the normal gain would be minus RF over R1. For the positive limit, RF parallel to R4 over R1, and the negative limit, RF parallel to R3 over R1. For the positive limit, if you do superposition on these two nodes, you can get your L plus and L minus equations like this, and typically you will choose your L plus and L minus to have the same absolute voltage. So R4 and R3 will be the same value, and R5 and R2 will be the same value, making these two gains the same and making these two equations look the same, making design much easier. Okay, so you only need to use 3 of the 5 equations with symmetrical limits. Right, so time to implement these equations and see what you can come up with. So I want you to design a non-linear limiter circuit to have a gain of 2 when there's no limiting happening. Okay, so just RF over R1. And then limit the output voltage to plus minus 5 volts when you have plus minus 10 volt rails. Okay, so looking at this equation, this plus and minus V is the rails, and VD is the diode on voltage. Right, and limiting plus and minus is where you want your output to be stabilized at. Okay, so the limiting gain should be 0.125 volts per volts. So when these two resistors in the middle is included, the gain should drop to 0.125. Okay, and I say use silicon diodes. So start by choosing resistor 1 and work your way from there by computing all of the other resistors and choose E12 values. After that, simulate the problem. Okay, and then I want you to implement this limiting circuit on a Wien-bridge oscillator and also simulate it. Okay, and I want you to limit the gain to 1.8 volts per volts. And do this for plus minus 5, plus minus 4, and plus minus 3 volts. And note that the limiting for a Wien-bridge is non-inverting. So you're going to have to adapt the equations a tiny bit, but I will show you in the solutions. But see if you can figure it out yourself first. Okay, so pause the video there and go try this first limiter out. So the gain without limiting should be 2, so RF over R1 inverted should be equal to minus 2, and we can select 10k and 22 kilo ohms. Okay, then L plus should be equal to absolute L minus equal to 5 volts, with the assumption that resistor 4 and 3 is the same then, and resistor 5 and 2. We can find the value of resistor 4 by equating this to minus 1.25. We have RF1, RF and R1. So this works out at 1.2 kilo ohms. Okay. So with that, our limit should be 5. Our rail is 10. Diode switches on at 0.7. We have R4 from our previous calculation, and we can find R5. And this works out at 2.7 kilo ohms. Okay, so that is the first non-linear limiter. So let me jump into the simulator and show you that this does work. So here is our non-linear limiter, and I built it using two signal diodes. And first off, I'm going to run it with a 6 volt sinusoid at 10 kilohertz and see if it actually does limit the circuit. The signal that you're going to see is not going to be so pretty anymore. It's not going to be pure sinusoidal because this is meant to bring oscillators into check. So if we run this, there is our input and there is our output. Okay. So yeah, it does try to limit it at 5 volts. So we have 5 plus 0.7 of the diodes left here. So it does actually limit the gain when our signal becomes too large. Okay, but as I said, this is a bit more applicable to oscillators when limiting the gain on those, not necessarily like we are doing it here. Okay, so let's do a DC sweep of this, and just double click the output here. If our input is extremely large, our output will be at 6 volts. Okay, so if we take the gradient in this top part, we will see that our slope is 1.36. Okay, so for our resistor selection, that is very close to the minus 0.125 that we wanted initially. And down here, we have the same. And in the middle of our resistor choices, we should see our gain being 2.2. Okay. So yes, our gain is being limited at different voltages. And between output of plus minus 5 volts, we will see that our output will be limited. Okay. So the circuit for any input from 0 to 2 volts will not be as harshly affected. Okay, so these nonlinear limiters is mainly based on the output signal. Okay, so to insert something of 3 volts, we will see the limiting and the distortion won't be so bad. So let's try that out quickly. Best way to learn these circuits is to play with them. Okay, so there you can see that this is kind of limited at 5 volts. So as our input increase, this will go closer to the 6 volts that we had. Okay, so this is our inverting limiter circuit. Let's go to the presentation and look at the solution for implementing this with a Wien-bridge. Okay, so for the non-inverting limiter, like we have with the Wien-bridges, we should remember that our gain is RF over R1 plus 1 is 3. Okay, so the gain there is not 2 anymore. And we need to adapt our equations a little bit. And I've done it in here. And basically, you have a limit divided by the gain to do a correction from inverting to non-inverting configuration. So if we multiply our voltage, our rail, and our VD with the final gain that we want, then we get that our resistor is 1.8 times larger. Okay, so the gain that we have here. And this is not in the textbook, this is not on any internet website that I looked at. So the Wien-bridge needs some adapting from what you will normally find for the equations for these non-inverting limiters. Okay, most people will just go with the inverting, design it, and the output values does not work out correct, and you increase some of the resistor values and they are fixed magically. So the ratio is actually the gain that you have here to fix it. Okay, and as I said, that is because the limit is technically divided to flip the curve. Okay, so For a Wien-bridge oscillator, RF over R1 plus 1 should be equal to 3. So R1 and RF has the same ratio of 10 over 22 kilo ohms. So we will have our oscillation starting. Limiting at plus minus 5 volts. Okay. And just add the plus 1 to the RF parallel to R3 and get rid of the minus sign, and this should be equal to 1.8. Then calculating R4 and R3 should yield 12 kilo ohms. Adding the gain and the 12 kilo ohms in here, R5 and R2 will end up to be 56 kilo ohms. If you just take the normal approach of designing the inverting kind, you will end up with 50 kilo ohms. Multiply that answer with the gain, and that will be the right one to add in your circuit. Okay, then you can redo this calculation for 4 volts and 3 volts, and you will end up with 68K and 100 kilo ohms. So let's go over to simulation where I can show you this limiter working. So here I have a Wien-bridge set up. The only resistor that change is R2 and R5. So 22K, 12K, our oscillations will start, and let's see if our limiter kicks in at the right value. So that is 5 volts, 4 volts, and 3 volts. Let's run this. And where is our outputs? 3 volts, 4 volts, and 5 volts. So our limiter is working perfectly. Looking at these circuits, signals, you will see that they are a bit distorted due to the diode that we are using, but they are not clipping anymore, so they will be a little bit more pure. And where is our FFT? You can see the different signals and how the noise will be added here. Okay, so that is Wien-bridge with limiting. Let's look at some more or other limiting implementations. So here I have two alternatives. The moment that the output becomes large enough to overcome the Zener voltage and the diode voltage, so for a positive signal we will have Zener 2 here and diode 1, and for a negative signal we will have Zener 1 and diode 2. Okay, so it's basically the Zener voltage plus 1 diode voltage. So that is when this circuit will trigger. Okay, and then RF will become in parallel with R4. Obviously plus the parasitic resistances of these two diodes. Okay, so this is a quite easy way to limit the output, but sometimes you are limited to the amount of Zener voltages that is available and costs and whatnot. Okay, so choosing these two the same Zeners, you will have a limiting of which is symmetrical. Okay, next implementation is to take some LEDs. In the simulation I used 5 volt LEDs, so they will switch on at 5 volts positive and negative. So this is for positive waves and this one is for negative limitation. Okay, so this will limit our output at a little bit more than plus minus 5 volts. Again, R4 in parallel with RF when this limiting is happening. Okay, so let's jump over to the simulations of these two and show you how they are working. So here is my two implementations. The Zeners here in the first one is 4.7 volts for the breakdown. So this first circuit should have a plus minus 5.4 volts output, and the LEDs here has on voltage at about 2.5 volts. So we should see plus minus 2.5 volts at the output for these LEDs. Okay, we open this. That is the breakdown voltage, so it won't limit to 5 volt. That is when the LED breaks. But yeah, so the limiting here plus minus 5.4, the limiting here plus minus 2.5. Let's run this. About 5.4, a little bit higher due to the parasitics. And this one over here, 2.5. Okay, so we can also switch this out with, let's say, two signal diodes like this. And can you guess where this will be limiting the output to? If your answer was 0.7, that is very incorrect. It will limit a bit more to the 0.5 side, because these diodes switch on at 0.6 rather than 0.7, but a diode will switch on technically much earlier, more or less at 0.5. We only see the linear curve of our linear-ish part of our transistor's current curve past 0.7 volts. Okay, but the the diode is on long before that. Okay, and this is making use of the non-linearity of our diodes, which starts at more or less 0.5 volts. Okay, so if you want the 1 volt peak-to-peak signal, you can just implement diodes like this. Want something larger, you can use Zeners, you can use LEDs in here. Basically anything that has some voltage where it switches on. So you will also find that people use some triggering circuits in here. There is a lot of ways to do this. But these two are by far the simplest. Okay, that is it for nonlinear limiting. Thank you for watching.